In section 2.1, we're going to take a look at sets, and this section actually has lots and lots of definitions. So we're going to look at definitions and examples. The first definition we have is the definition of the word set. And basically a set is just a collection of objects called members or elements. We can have all kinds of sets. So in example 1, we can see that we have the set of the days of the week, Sunday through Saturday. In example 2, we just have a set of fruit. In example 3, we're looking at positive even numbers. And in set 4, we're looking at multiples of 5, positive multiples of 5. Another term that we have is something called the null set. It's a set that has no numbers. We can look at it and see that we have empty brackets, or another way to represent the null set would be to use this symbol here that we'll take a look at again. So it's like a circle with a line through it. In example C, we have the set of counting numbers. Those are numbers that we begin with 1 and go on to infinity. We use a capital N to represent the counting numbers. And then in set D, we have a very similar set. It's called the set of whole numbers. So the set of whole numbers are counting numbers, and 0 is included in there. And we actually use a letter W to represent the whole numbers. We can compare sets. We can say that two sets are equal when the two sets have exactly the same elements. So the definition says two sets are equal if and only if, oh that's weird, if and only if, we just studied that. Two sets are equal if and only if they contain exactly the same elements. So set A has the elements Monday, Wednesday, Friday. Set B has the elements Wednesday, Monday, Friday. They have the same three elements, different order, same three elements. So we would say that sets A and B are equal. In example 2, we can see that we have F is equal to 1, contains the numbers 1, 5, and 8. Set G has the same elements, 1, 5, and 8. So because they are absolutely identical, we would say the two sets are equal. A term that's similar to equal is the word equivalent. Two sets are equivalent if and only if there's a one-to-one correspondence between the sets. And so basically it means we can match up each element to another element in the set. They don't have to be identical. They're going to have the same number of elements. So if we take a look at set A, we have blue, black, and brown. We have 3 elements. In set B, we have 1, 2, 3. 3 elements as well. So we would say that A and B are equivalent, and we can use this symbol here with the arrow going in both directions. We can say A is equivalent to B. If we look at set C in number 2, we have the months, September, October, November, December. So we have 4 months listed. In set D, we have A, B, C, and D. Again, 4 elements in this set. Because the two sets are the same size, they have the same number of elements, and we can match A with September, B with October, C with November, and D with December, we can say the two sets are equivalent. C is equivalent to D. So we're going to take a look at a variety of sets and try to apply the definitions. In this practice, we want to name all the sets that are equal and all the sets that are equivalent. So if we first look at equal sets, we want to find sets that are absolutely the same. So if we go ahead and look up here, we have 1, 5, 7. Do we have any set here that has the numbers 1, 5, 7 in it? We have 5, 9, 1, 7. So it looks like set A and set G are equal to one another because they have the exact same elements in it. If we go to set B, green beans, zucchini, broccoli, peppers, I don't see any other set that has those same vegetables. If I go to set C, I see A, B, and C. Set D has C, A, B. C and D have the same number of elements and actually the same elements, just in different order. So I can say that set C is equal to set D. If I move down, I can see red, yellow, blue. So it has 3 elements in it, but I don't see any other set that has those same 3 elements. 2, 4, 6, 8, I don't see any other set. So my equal sets from what I'm given here are A and G and C and D. We're going to move on to equivalent sets. Remember, equivalent sets are sets that have the same number of elements, but they can be different elements. So I can say that set A has 1, 2, 3, 4 elements in it. It's going to be equivalent to set B, 1, 2, 3, 4, because it also has 4 elements. I can say that set A is also going to be equivalent to another set of 4, which would be F, 2, 4, 6, 8. It has 4 elements. And then I can say that set A is equivalent to set G. It has the same number of elements. So 2 sets can be both equal and equivalent. If the sets are equal, then they're equivalent. If they're equivalent, they might not necessarily be equal. So then if I go to my set B, green bean, zucchini, broccoli, I saw that it was equivalent to set B, but it's also, with its 4 elements, equivalent to set F, and B is also equivalent to set G. If I look at set C, C has 3 elements in it. I can say that it's equivalent to set D because it was also equal to set D. I can say that set C is also equivalent to E. And I can say that set D is equivalent to E. And did I miss anything else? I believe I'm missing set F is equivalent to set G. We have a lot of equivalences here. So when we're comparing sets, equivalent means they just have the same number of elements, where equal means they're absolutely identical. Moving on to some more definitions, we can define a set as either being finite or infinite. A finite set means that that set has a set number of elements in it. We can count the number of elements and they stop at a particular number. So when we look at the set of days of the week, we have Sunday through Saturday, we can count how many elements this is. We have 7 elements in our set. In the next example, I'm looking at a set and it looks like I'm looking at counting numbers less than or equal to 5. So I have the set of 5, 4, 3, 2, 1. My set only has those 5 elements in it, so we would say it's finite. In the third example, I have a set that has a scattering of letters. I have A, B, C, D, E, W, X, Y, Z. Again, I have just this limited number of elements, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 elements in my set. These are all examples of finite sets. They have a starting element and an ending element, and I can count the number of elements in between or inside that set. An infinite set is a set that contains an infinite number of elements. This is my symbol for infinity. And so when I say an infinite number, it means that it just keeps on going. I don't have an ending, or I possibly might not have a beginning for my set. So some examples here are the odd numbers, 1, 3, 5, 7, 9, and it keeps on going. So this ... is going to tell me that my set is continuing to go on. Example 2 is a set of rational numbers in the interval from 1 to 2. So this set does have a starting and a stopping, But if we look at the numbers between 1 and 2, anytime I find a number, so for example, between 1 and 2 I can find the number 1.5, but between 1 and 1.5 I can find 1.25. Between 1 and 1.25 I can find another number like 1.15, and so on. So I can just keep always finding a number in between. So between the numbers 1 and 2, I actually have an infinite number. I can keep on dividing my interval up, and there's always a number in between. So even though I have a starting and a stopping, if I was to try to list all the rational numbers in between there, it would be infinite. So this one here is kind of a hard one to grasp, but between 1 and 2 there's an infinite number of rational numbers. I can always find another one. 1.1, 1.11, 1.111, 1.11111. So it just keeps on going and going. The third example of an infinite set is the set of whole numbers. 0, 1, 2, 3, 4, and that goes on to infinity. And again, we represent whole numbers with a W. So let's practice this. We're going to look at some different sets and determine if those sets are infinite or if they are finite. So in set A, it's the set of numbers greater than 99, set of all numbers greater than 99. So this set would look like all numbers. So it could be 99.001, and it could go on. 99.35, 100, 105, like it just keeps on going. So in this here, because it says all numbers, we're going to classify that as our real numbers, so it's going to have rational numbers in there, irrational numbers, it's just all real numbers. So this here is definitely an infinite set. It would go on forever. Set B says the set of counting numbers less than 12. Well, if we're talking about counting numbers, our first counting number begins with 1, and we're looking at numbers less than 12. So the set could look like 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that's my set. So my set actually has a total of 12 elements in it. Because it has a set number of elements, we're going to say that it's finite. In C, we're looking at the set of red fruits. So I could list out my red fruits. I have apples, I have raspberries, I have watermelon, they're red inside, I have grapes. So I might have a long list of red fruits, but it's going to end because I can just list them out. I can count the number of red fruits I have. So we would say that that is finite. So I can count it, and it will end at a particular number. So there might be 25 red fruits. In example D, it's the set of students in Math 103. So with this set here, I could just list out the students in my class. I have Jasmine, Bryce, Meredith, Olivia, Ben, Michael, and I can go ahead and just list out all the members in that set. I actually have 18 members in Math 103. So because I have a set number of elements in my particular set, I would say that it's finite. There's a finite number of students in Math 103. The last set is the set of prime numbers. So a prime number is a number whose only factors are 1 in itself. So our first prime number is 2. 3, 5, 7, 11, 13, and this set continues to go on. So this set, we don't really have an ending. We could always find another prime number down the road. So we would say that this particular set is infinite. So in the examples here, we had two infinite sets. The set of all numbers greater than 99, because there was no limit to that. We can go starting at 99 and keep going on forever. And the set of prime numbers starting at 2, going on forever. The other three sets were finite because we had a starting and an ending, and we could count the number of elements in between. Even more definitions. Like I said, this section has lots and lots of definitions. The first definition we're going to look at here is universal set. A lot of times we'll be given what the universal set is, and it's going to be the set that contains everything we're considering in this particular situation. So the example we have here of our universal set is the days of the week. So we're looking at all 7 days of the week. This is our universal set. If, for example, we were looking at the days of the week that a particular class is offered, maybe a Monday, Wednesday, Friday, we can say set D is equal to that particular set, Monday, Wednesday, Friday. Then we have something that's called the complement. The complement of D would be the set of elements that are in the universal set that are not in our particular set. So the complement of D is everything left over. So here's my set D, Monday, Wednesday, Friday. The complement of D would be all the other days of the week left over from my universal set. So because set D contains Monday, Wednesday, and Friday, my complement of D would be Sunday, Tuesday, Thursday, and Saturday. I should be able to take the sets in set D and the complement of D, and if I put those two sets together, they should give me my universal set. Let's look at another example. Here the universal set is the set of whole numbers from 0 to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Set E is the set of even whole numbers from 0 to 10. So my set E is evens. It would be 0, 2, 4, 6, 8, and 10. If I wanted the complement of E, to write the complement of E, what we do sometimes, instead of writing the word out, we just put a line over the top of it. That means complement. So the complement of E would equal everything that's left over. So my set E had the elements 0, 2, 4, 6, 8, and 10. The complement then would have the set 1, 3, 5, 7, and 9. Again, when I bring these two sets together, so if I was to combine E and the complement of E, they should actually bring me back to my universal set. Finally, our last set of definitions. Here we have the definition of subset. So a subset is part of an initial set. So the set A is a subset of B if and only if every element in A is also an element in B. So set A is part of set B. It contains some, if not all, of the elements in B. So if we look at an example, which of the following is the subset of one-digit whole numbers that are even? So let's first look at what that set looks like. So if we're looking at the set one-digit whole numbers that are even, We have 0, 2, 4, 6, 8. It's going to end at 8 because we're looking at just one digit whole numbers that are even. So we want to figure out which of these smaller sets is a subset of 2, 4, 6, and 8. 0, 2, 4, 6, 8. So here I can see that A has 2, 4, and 6 in it, so A would be a subset. In B we have 3, 5, 9, that's odd, so that's not a subset. 8 and 10 is close. It has 8, which is a subset of my set I'm looking at, but 10 is not. So it's not 8 and 10. And then the final one is set 0. And 0 is a member of my set, so we could say that that is a subset. So 2, 4, 6 is a subset of my initial set, and 0 is a subset. Let's look at another example. Which of the following is a subset of students in Math 103? So I want to think about my Math 103 students. In the first set I have Olivia, Shanna, Ben, and Garrett. Yep, those 4 students are in my class, so I would say that that's a subset. In B, I have Ryan, Christian, and Mike. Christian and Mike are in my class, but Ryan's not, so that's not a subset. And then part C is the empty set. The empty set is often included as a subset. So of my set, I can also have nothing in it, and that would actually be considered a part of my set. So A and C are considered subsets of Math 103. The last thing I have here are some different symbols. We talked about the null set. The null set looks like a 0 with a line through it. We have 2 ways to name subsets, a proper subset and a regular subset. And it looks like a sideways U when we do that. If we say that something's not a subset, we would put a sideways U with a line through it. And when we say element of, it looks like a weird E. So for example, if I have if I go back to my whole numbers, I can say that 2 is an element of my set. An element is just pulling it out. It's not saying a set of numbers, it's just saying I'm listing one of my elements. 2 is an element of the set, where I could say that 2 is also a subset of my set. The difference here, though, is that when I talk about a subset, I'm going to see that my 2 then is going to be inside brackets. So I can tell that I'm talking about a subset because I have brackets, where in the one above, the 2 does not have brackets. It's just an element of. So those are our notes on section 2.1. There's lots of definitions. If you go and check out the Nearpod I have up in Moodle, it'll give you a little practice identifying some of those key definitions, like infinite and finite, complement, subset, and just determining if sets are equal or equivalent.